All right, algebraic reasoning. Today we're going to be talking about polynomial functions and models. And so, first off, what is a polynomial? Polynomial is an algebraic expression that can be written as an x to the n plus a sub n minus 1, x to the n minus 1, etc., etc. So just to be clear here, I am reading from here, okay, where n is a non-negative integer, x is a variable, and each a is a constant called a coefficient. So this is a lot to unpack here. It sounds very confusing, but it's actually pretty straightforward. Essentially, numbers like, or expressions like 5x cubed plus 4x squared minus 3, these are examples of what are called polynomials. So insofar as your exponent is a non-negative integer, so as long as these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 0, you're okay. Notice 3 is actually the same thing as 3x to the 0 because x to the 0 equals 1. X obviously is a variable, and you have a constant called a coefficient. So keep in mind that these coefficients, like if you have 5 over 2, that's fine. If you have 1/4, that's okay for the coefficient. It's just the exponent can't be anything but an integer. So again, integers are positive, negative, whole numbers. Here we're talking about non-negative integers. So that would be 0, 1, 2, 3, 4, 5. Okay? So the non-negative means 0, 1, 2, 3, 4, 5, etc. Okay? Also, they could have just said whole numbers, right? The coefficient a to the 0, a sub 0, is called the constant term. So we kind of alluded to this earlier, that the number by itself is always going to be the y-intercept. And the reason why this is the case is if everything else has an x, the y-intercept is when x is 0, so all of those will go away, they'll be deleted out, and the only thing you'll be left with is the constant, and that's the y-intercept. Okay, so here we go. What are the characteristics of polynomials? They're all whole numbers. We just mentioned that earlier here. No variable is contained in the denominator. So what that means is you can't have a negative, right? Because we know if we have something like x to the negative 3, that's the same thing as 1 over x cubed, and that would be a variable in the denominator. So that makes sense. No variable is under a radical. So that just means you can't have like x to the 1/2. Okay, this goes back to it's a non-negative. So you're aware of that. Any letter may be used as a variable in the polynomial. So in other words, if you had z cubed plus 3z squared, that's still a polynomial. And they can only have integer exponents. Okay, so these are actually kind of like restating the same thing over and over and over again. Okay, so here are examples, and we can see that these are all okay. Wanted to realize that the last one, 19, is the same thing as 19x to the 0. Just wanted to point that out. Here are examples that are not polynomials. Okay, and we can talk about why each of these are not. And this is where it's important. So this is not because of the negative 2. This is not because of the 1/3. This is not because of the square root. Remember, we said the square root of m is the same thing as m to the 1/2 power. We can't have that. And this right here is the same thing as p to the negative 1. Again, we can't have that. They have to be 0, 1, 2, 3. The exponents have to be 0, 1, 2, 3, 4. And that's really what you're looking for. You're just looking at the exponents. Okay. We also want to stress here that we can talk about the degree of the polynomial, and the degree is just the highest exponent. So the highest exponent here for the first one would be 4. The degree here would be 12. The degree here would be 1. Notice there's still a 1 there. And this is just 19. So this is called a constant. Okay, just want to stress the vocabulary here. And so it's saying provide examples of each. Okay, so linear just means it's like a line. You all are pretty familiar with this. Y equals 2x minus 1 would be an example. Quadratic, which means you got some form of x squared, so like 3x squared plus 2x plus 1 cubic means your degrees goes to 3, so x cubed minus 7. Quartic is 4, x to the 4th, quintic is 5. And it doesn't matter if I put terms here or not. We'll go 8. It really doesn't matter, okay? It's just, again, these names are based upon the highest degree, okay? On to the next one. 0, X-intercept solutions, roots, and factors of polynomials. So we let f of x be a polynomial if r is a real number that satisfies any of the following statements, then r satisfies all of the statements. Then all of the following are equivalent. So r is a 0 of the function, r is an intercept, x-intercept of a graph of the function, x equals r is a solution or a root of f of x equals 0, and x minus r is f of x. There's a one-to-one correspondence between the linear factors of f of x that have real coefficients in the x-intercept. Okay, so this is a very fancy way of just telling you that when you see a 0, like let's say x equals 2 and x equals 3, okay? These are, if your solutions are x equals 2, x equals 3, well, what we can notice is that if we subtract 2 from both sides, we get x minus 2 equals 0. If we subtract 3 from both sides, we get x minus 3 equals 0. And so because of this, we can put these together and say x minus 2 times x minus 3 equals 0. And if you don't believe me, well, if we're saying at least one of them is 0, this statement here, this statement right here, has to be true, right? So all that we're saying here is if we say we have zeros or we have solutions, all of these things are kind of just alluding, all of these things are just kind of alluding back to the same sort of property, okay? Which is what I'm writing here as an example, okay? And I think a lot of this will come together when we start doing actual problems. So polynomial functions of odd degrees. When the degree of a polynomial f of x equals a x to the n is odd, its graph has a basic shape. So this is very confusing the way it's shown here, or can be. But all we're saying here is if I give you, for example, y equals x cubed, if you plug in a very, I'm going to use language that's not 100% exact, but a very big negative number inside x cubed. So if you plug in a negative number inside x cubed, then what ends up happening is that your result is going to be, whatever it is, it's going to become a negative number, right? Because a negative times a negative times a negative is a negative, okay? So what that means is that this thing, for very large values, is going to live in the negative. By the way, it doesn't matter if I tack on other values, because if x cubed is the largest, for very large numbers, and this is the power of exponential growth, everything else becomes irrelevant, becomes superfluous. X cubed impacts the number way more than any 2x squared, any x value, or any constant. So this is the power exponential is way more powerful than all the other powers, so the number will grow. So like if I put in a million, x cubed to the million is going to be way bigger than a million x cubed. A million cubed x cubed. A million cubed is going to be way bigger than a million squared. And so that's what I'm arguing. But all we have to do is think, when we attack these problems, is plug in a negative number. We'll see that the value will become negative. If we plug in a positive number, then we'll see that we'll end up getting a positive value, right? And that's what this is saying, okay? Now, if the leading coefficient is negative, then it basically just flips it, right? Because if we think about it, if you have a negative x cubed, right, and then we plug in a negative number, right, you're going to get, we said earlier that this piece is going to give you a negative, and a negative negative is going to be a positive, okay? And the same argument would hold for the other side, right? So if we put in a number squared, a positive number squared, Well, you're just going to get a negative number. And that would be, so that's why this one starts off positive, this one starts off negative. You also see it's a reflection, okay? So one of the things that I think that's important to realize is that you do not need to memorize this. You can literally just think, if I plug in a really big negative number, what happens? If I plug in a really big positive number, what happens? And that will get you these. And what I'm concerning myself with is what's called end behavior. It's how these graphs, this is called end behavior. Okay? And this is these lines in the notes. That's what's going on here. That's what we're referring to. So these parts here. These parts here. Okay? And we'll talk more about this in a little bit. Okay. Let's move on to the next slide. Even. So what happens with even? Well, if we have a negative number and you square it, well, anytime you square something, if it's an even number, if you can pair them up, you'll get a positive. So irrespective of whether it's negative or positive, you're going to get a positive, and that's why this thing opens up. On the flip side, if you have a negative x squared, a negative even power, you would, if you plugged in a negative, again, it doesn't matter, it would come out as positive, but because we have a negative sign in front, this thing would start off negative, and the same argument would hold true if you plugged in a positive number, because then you would just end up with, again, a negative. So, again, these kind of tend to make sense. The other thing that's important here is to realize this function bounces off the x-axis. So what do I mean by that? It means it hits the x. Anything that's even doesn't cut through. It hits and it bounces. It hits and it bounces. So, okay. Properties of general polynomial functions. Every graph of a polynomial function is smooth and continuous. What that means is that the definition of continuous means the simple definition of continuous, I should say. These can get very complicated if we want to get super technical, but keeping it simple. Just think of it as your pen. If you write across with your pen, you don't lift your pen, then it's continuous. Okay, so if you have a break, okay, or you have a hole here, then this is not a polynomial function, because all polynomial functions are continuous. If you have a cusp, which is kind of like a sharp point, then it's not a polynomial function. So again, looking at this here, polynomial functions are smooth and continuous, and again, smooth and continuous. Intercepts. Consider a polynomial function of the form. You see what the form is? The Y-intercept is so this is rehashing it. The X-intercept of f are real zeros of f. Every polynomial has exactly one intercept. If the number if X-intercept is limited to the degree n of the polynomial. Okay. So some facts. Multiplicity. So if you have something that repeats, like something like x minus 3 cubed, then what we have is a multiplicity of 3, because it repeats itself 3 times. Okay, x minus 4 to the 7th would have a multiplicity of 7. What's important here to realize is that if it's even, it bounces off, and if it's odd, it passes through. These are the rules that we're going to use, and I'm trying to quickly go through it because I think an example makes more sense. So here's an example. So find all the zeros of f of x equals x plus 1 cubed, x minus 1, x minus 3 quantity squared. State the multiplicity of each zero. State whether the graph of f touches or crosses through the x-axis. Then sketch a graph. Okay, so we know, I'm going to actually start with the graph. We know that this is going to cross at -1 from here, 1 from here, so notice it's the opposite, and then 3 here. Okay, so what you do, this is, we know it's crossing, we need to figure out end behavior. So end behavior means that we're going to look at what is the highest power of each of these. So this is x cubed, this is x, and this is x squared. If we multiply all of these together, it means we're adding the exponents. So we do 3 plus 1 plus 2, which is x to the 6. Okay, this is the degree. That's the highest power. And so what I'm really saying is that if you FOILed that out, you would start off by multiplying every x by every x, and that would get you the highest power. And so it's x to the 6. This is even, which means if I plug in a negative value in for x at extreme values, a negative number to the 6th power would become positive. So we know that this function starts off high, positive. It's approaching -1. Now, -1 is the one in yellow, which when I underline, it says it's cubed. And so what happens if it's cubed? It crosses. So it crosses, and then we'll slowly have it come back, and then it hits x minus 1, which is going to be the green. Now again, x minus 1 has an odd index of 1, so that will also cross. And the interesting part is the last one, though, is even. So when it's even, it bounces. So your picture should look something like this. Okay. And so that's essentially the graph. Now, if we want to find the Y-intercept, notice that on the back side you would have ended up with 1 cubed, -1, and -3 squared. So if I put all this together, it's 1 times -1 times 9, which says that this point that it crosses, the Y-intercept is -9. So if you pay attention to these, and the negative sign here matters, then that will give you the Y-intercept, which is -9. So this is giving me the Y-intercept. Okay, and again, if you think about FOILing this out, if you were to write the whole thing out, the very back would be the product. The product of the very last terms would be the constant, right? Because you're multiplying everything by everything. So it's pretty much it. Again, remember this cross here, touches. I like to say bounce, but touches. Okay. All right, local extrema and inflection points. So extremas refer to the local maxima or the local minima of the polynomial. So this would be like here. There's a local max here, a local min here, a local min here. Local extrema occur where the output values have changed from increasing to decreasing. So going back to this example, we can see we're decreasing and then suddenly increasing. We're increasing, then we're suddenly decreasing. And then the last one, this is hard to see, but we're right here. We're decreasing and then we're increasing. Okay. A polynomial of degree n has at most n minus 1 local extrema. So if you have the degree, then n minus 1 would give you the local extrema. And this is kind of intuitive. So where you cross, let's go back. This picture you're crossing here, here, and here. So it has to turn, right, to get back here. And it has to turn to get back here. So you're always going to have one less. I should say at most one less, because you could not have that at all. So at most you'd have, because you would have to change direction. Okay, an inflection point occurs when it changes concavity. So what does that mean? So concavity, this is concave down. This is concave up. When it changes concavity, so if it's like something like this, it's changing somewhere here from concave down to concave up. That concavity, that is called an inflection point. These terms are incredibly important as you progress through mathematically. Okay? And you could also have it flipped. So you could have something like this, and this would also be an inflection point. So this is going from concave up to concave down. Okay. A polynomial degree n has at most n minus 2 points of inflection, and a polynomial function of odd degree with degree n greater than 2 has at least one inflection point. Okay. All right, so find a complete graph of such. So this is actually asking us to graph this on a calculator. So 1 second. And so here's the graph, and what this is just trying to show you that is if you had zoomed in on a particular point, you may not have seen everything that's going on, okay? And we know this to be kind of the case because if we look at these numbers here, they're pretty big. But that's all that they're trying to stress here. So this is where we really get into what's important here. So we want to sketch the graph of the function using what we know about the function's degree, its end behavior, its zeros, multiplicity, and y-intercept. Okay, so how do we go about graphing something like this, right? That's the real question. So we know, let's just draw an xy plane. We know this one crosses at 7 and then -3. We know it crosses at 7 because if we say x minus 7 equals 0, 7 minus 7 is 0, and -3 because -3 plus 3 is 0. So those are our zeros. We definitely have those. We know that if we multiply 3 by -7 by 3 squared, so these are like the back ends, this was going to give me the y-intercept. So this would be 3 times -7 times 9, which is -63 times 3, which is -189. So this is going to be a really small, like it's going to go really low, right? So we know the y-intercept there. So this is giving me the y-intercept. Okay. What else do we know? Well, we can find the end behavior. So the fancy way of saying this is we say as x approaches -infinity, f of x approaches what? So we can see here that this is squared, this right here is squared, and this is x. So this whole thing, the leading term, would be 3x cubed, okay? And so with 3x cubed, if we plug in a really big negative number, what happens? Well, if you plug in a really big negative number, because it's odd, you're going to get a negative value. So this should be approaching -infinity, but if we use infinity, we're going to get to another infinity. So we know that this thing starts off in the negative, it's going to be negative, and in the end, it's going to be positive. Okay? So let's see here. What else do we have? We have, so we know degree and behavior. We have its zeros. We need multiplicity. So what do we know about multiplicity? Multiplicity, the -3. So what happens here is this thing, it's going to hit this, but because the x plus 3 is squared, that means it's going to bounce. It means it's going to go down here. And I don't know. Maybe it immediately turns, or maybe it goes down a little bit and then turns. I don't know, but I know eventually it's going to go up. And it's going to cross through 7 because x minus 7 is odd. And it's going to look something like such. Okay? So this would have a multiplicity of 2. This would have a multiplicity of 1. Okay? And that's it. Okay. Let's get another one. So again, let me draw an xy plane. We know this crosses at 3. This crosses at -4. And we just kind of play the same game. So again, if the y-intercept is going to be if I multiply 2 times -3 times 4 cubed. So this is going to be, these two is going to be -6. 4 cubed is 64, which is what, 24, carry the 2, 36, 38. Again, -384. That's what the y-intercept is going to be. So we know we have a really low value of -384 is where it's going to cross the y-axis. We also know that as x approaches negative infinity, f of x approaches. So if we look at this, we're going to have x cubed, so this is going to be 2x to the fourth. So this one's even, which means that whether it's negative or positive, it's going to always come out as positive, right? Because a negative times a negative is a positive. So if you're pairing things, then they're always going to come out as positive. Okay, so we know this is going to end up high, and this is going to be high. Okay, now we know with both, actually we know with both of these, because they're odd, that means they're going to cross through. So this is going to cross through. It's going to go down here. Again, I don't know when it's starting to pop back up. It actually could drop. It could actually drop here and then go back up as well. So we don't know that. If you wanted to be super specific, you could plot points to figure it out. But this is sufficient for what we're trying to do. We're just trying to see a sketch of what the graph would look like. It's going to look something like that. Okay. This one has a multiplicity of 3. And actually, when it crosses here, technically, it does actually cross almost like a cubic. Just FYI. And this is linear. So when it's linear, it just almost just cuts through. And so this has a multiplicity of 1. But that's just all that's going on there. Okay. So next one. So the next one, they're trying to make it a little bit more complicated, but all we need to do is, what we realize is we can factor out an x. So we have 4x. This becomes x squared minus 3. Okay. So if you wanted to, you can do the difference of squares, and you would get x plus 3. I'm sorry. X plus the square root of 3 and x minus the square root of 3. So now we know that this thing crosses at 0. 0 is coming from here. Negative square root 3 and positive square root 3. Okay, and that's from these two. Okay. And so when we draw this one, it's nice because it already tells us that it's cubic. So this means as x approaches negative infinity, if you plugged in a negative number, you would get a negative times 4 is a negative. So that means f of x would be a negative. And as x approaches infinity, f of x is infinity. So basically, if you plug in a negative value, it comes out negative. If you plug in a positive value, it will come out positive. So what that means is it starts off negative and it ends positive. Now, again, these are all odd, right? These are actually all 1. So this is just going to cut through. It's just going to cut through here, it's going to cut through here, and it's going to cut through there. It'll look something like that. Okay. Again, specifics, I don't know. If I want to know, I can always plot more points to figure out specifics, but this is sufficient. All of these have a multiplicity of 1. Okay, and on to the next one. So, once more, x squared is at 0, and we have 2 and negative 2. If we multiply these all together, we get x to the 4th. And what that tells me is that as x approaches negative infinity, f of x is going to be positive. And as x approaches infinity, f of x is going to be positive. Because if you're pairing things, they're always going to be positive. I only have 45 seconds left, so I'm going to go kind of fast here. By the way, if we multiply this, you're going to get negative 4 is the y-intercept. So this one's going to go something like wait, I made a mistake here. Sorry. This is going to cross at negative 4. This is going to cross at here. So it's going to look something like so. Okay. All right. Ran out of time. I will continue this in the next video. See you guys.